since I was asked about that, you can find an equivalent formula for the probabilistic case. I don't have time to talk about it, but I believe this is a key formula if you do systems engineering, because according with this formula, you can have a much higher flexibility in the engineering work. So this ends my view onto state machines, and now I do something which goes, what I did so far was very much, I think, along the lines you always have if you do systems engineering. Now I go a step further and I talk about something which is a little bit more uncommon, which I call a functional view. And to explain why I'm interested in that, I will start with a little story. And it's a true story which was repeated by a number of people, and every time they repeated it, it was changed a little bit. So now you find the same story with a little bit of a different storyline. The true story was the following: at the end of the last century, so about 1998 or something, BMW was about to deliver a new premium car in their 700 series, and they decided they should have a handbrake which is electronic. Till then, the cars all had mechanical handbrakes, and now we can discuss for a long time whether electronic handbrakes are good or bad, and engineers have some ideas about that. But anyway, BMW decided now we are at a time where we can do that. And so they produced this electronic handbrake. An electronic handbrake is very simple. You have a button in the car, you press a button and the handbrake is activated. And of course now we are in requirements engineering. What is a good way to release a handbrake? Well, a simple thing is to push the button again. But that would be perhaps too simple or too inconvenient. A nice idea is that you push the handbrake when you are on a slope, and then you want to start again. And of course, people which are not very trained drivers, they always have the feeling, oh, this is a difficult situation, because if I do it the wrong way, the car will move back and so on. So what would be a nice idea to release the handbrake? You push the gas pedal, right? Wonderful, okay. This was the idea. Now, if you want to push the gas pedal to release your handbrake, you have to see how does the handbrake know that you push the gas pedal. Well, one idea would be introduce a sensor at the gas pedal when it is pressed. But another sensor is costly, and it is at a place where it is a dirty place. It can be a place where it gets wet. So perhaps it's not a good idea to introduce a new sensor. And now they said, well, we have a sensor at the torque of the machine, of the engine. And if the torque is increased a little bit, this indicates that the gas pedal is pushed and we can release the handbrake. So wonderful. And that's what it did. And thus they had a prototype car which was exactly like that. And one day, it was an automatic car, and one day the driver went down from the main campus of BMW, and to leave the campus he has to open a gate to get out. And it goes a little bit down, so he stopped and pushed the handbrake and opened the door to open the gate. When he opened the door, it was not like this today, it was a hot day in Munich, and hot air came into the car. What happens if hot air comes into the car? Yeah, the air conditioning control realizes that now the air in the car is too hot, and so the air conditioner starts to work. If the air conditioner starts to work, what happens? You need more energy.
Torque reduces.
Yeah, you push the torque a little bit because you need more energy. If you push the torque a little bit, what happens? You release the handbrake. This is a true story. In this case, it happened, but fortunately the driver, which was an experienced person, jumped into the car and could stop it. But for me, it was very interesting, that story. He told me that story at that time, and I thought about it. And what it is what I thought about, what we talk about now, it is called feature interaction. Whenever I say feature, I think functional features. And now a car has a lot of different functional features. Braking is one functional feature. Air conditioning is another functional feature. And now you get to the question whether these functional features are independent or whether they are dependent. And here we have a situation where we had a functional feature dependency between the air conditioning and the braking system. And I believe it's better not produce cars where you have a functional feature dependency, a feature interaction between air conditioning and braking systems. And this is why I'm now talking about this, and I worked for a long time on that, and I give you the solution, and the solution in the end comes up not so difficult, but we worked hard to get such a solution. It has to do with combining functions within one system. And this is another interesting observation, which is, by the way, a typical observation for cyber-physical systems. A lot of the cyber-physical systems are multifunctional. In the old days, there was only one multifunctional system, which was the Swiss Army knife. This was a multifunctional system which was proud to have so many different functionalities. With the introduction of software into our systems, we have a lot of multifunctional system. What is the ultimate multifunctional system? It's a smartphone. When I was young, a telephone could only be used to do telephone calls, nothing else. A radio could only be used to listen to radio, nothing else, and I could go on for a long time. And nowadays we have systems which are multifunctional, where you can do a lot of different things with the same system unit. This is true for the smartphone, and this is, by the way, also true for cars. We did some work a few years ago where we tried to count the number of functions in cars that are software dependent, and we came up to 4,000 or 8,000, something in between. It depends a little bit what you call a function. And this means that if you look at a car offers a high number of functions at the same time: air conditioning, braking system, light systems, acceleration, maybe there's an entertainment system, there is an emergency system, there are airbags, blah, 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 blah. And if you look at that, in a car today, you have between 10,000 and 20,000 different messages. Messages very much in the sense which I introduced this morning. And at every time interval, hundreds of messages go into the car and hundreds of messages get out of the car. They go into the car as signals by the sensors and, of course, as input of the driver, and they go out of the car as reactions of the system. So the window system is another functionality. And therefore, we have to, and if we want to, now think about, we write in an interface specification for the car as a system. I would not dare to give this as a PhD thesis to someone because it's completely impossible. If you would think about it, it would take, I don't know, a few thousand pages, just formulas to describe that. Nobody knows how much it is. So it's completely impossible. However, if you look at the single functions in a car, that would be not so impossible. For instance, for the handbraking system, to write a function for the handbraking system as such is not a big thing. You can write a state machine, you can write an interface assertion, not so much a problem. But as long as you put together functional features independently, which I do here, no problem. But then it's not possible to have any feature interactions. I told you about a feature interaction which is not very meaningful. Are there meaningful feature interactions? And the answer is yes, of course. There are many feature interactions. I will give you some numbers in the end. There are many feature interactions. I give you a simple one. If you listen to radio and you have a telephone in the car, if a telephone call comes in, then of course it is very nice if the the radio is turned down and the telephone is what you hear over the loudspeaker. This is a feature interaction. And this is a well accepted and specified feature interactions. And we have hundreds, thousands of feature interactions in cars today for very good reasons. Therefore, this wonderful idea, we specify the features independently, doesn't work because we don't know how to specify the feature interactions that way. Well, what we did now is we said we introduce what we call modes. And modes are basically internal channels in the system which describe the feature interactions. So if we would want to describe this unwanted feature interaction between the braking system and the air conditioning system, this would be the air conditioning system described as a function. We don't need that arrow because now we have an error, logical error, which tells if the air conditioning system comes in a particular situation, meaning needing more energy, which is not important that it needs more energy. From a logical point of view, it just means that in this situation for this incorrectly implemented car, it means that the braking system would come to a situation where it releases the handbrake. Of course, this is nothing we want to specify because it's stupid anyway. But if this would be the telephone and if this would be the radio, if a telephone comes in, the telephone would tell the radio, please turn down, and it would then put its output onto the loudspeaker. And if the telephone call comes to an end, it would tell the radio, now you can go on again. And this is how we model feature interactions. So given the isolated function, we introduce a refinement, which just introduces these additional channels. And with this refinement, we can combine it with other systems so we get feature interactions. And there is a publication in the Science of Computer Programming where what I'm telling you here is worked out in all details from a theoretical point of view. But we have done also some practical questions on that. And now let's look at that from the other way around. If we have a system and we want to decompose the interface of the system in a number of subsystems for looking at the particular sub-functions, how we do that. Because now to decompose the interface behavior of a large system, let's say a car, into a number of smaller things, what we assume now, we just decompose the interface in terms of channels. So here we have a large number of channels and large number of channels. Now we go to a small number of input channels and a small number of output channels. And we call now this syntactic interface a subtype of this interface if we have exactly this, and we write it like that. So we just consider at a small part, which to make it more explicit, if we look at a car, we just look, if we are interested in the handbrake system, we just look at the signals which are relevant for the handbrake system, which means operating the handbrake by activating it or looking at the results. What are the effects of the handbrake on the actuators? So that's how we do it. So from an overall syntactic system interface, we forget about a lot of the channels and just keep those channels. So we consider really a subsystem. And now we can have interesting questions at the level of behavior. Given such a syntactic subinterface, we can ask the question if we do the projection. And the projection is given the behavior function for the overall interface. So that is a behavior function for the whole car. Now we are interested in the behavior which is a projection onto the subsystem. It's defined here. It's not very difficult actually. We say this sub-behavior we get like that is for an input x prime, which is an input just for our braking system. We say we consider all the outputs we get by taking an overall input to the car with a property, if we restrict this input to the braking system, it is the input we are considering. And now we consider an output for the overall behavior, And here we take this output and we project it into the braking system. So in a certain sense, we say, well, we know the interface behavior of the whole car, but we project this down to the interface behavior of the handbraking system. And having this definition, we can talk whether the projection is phaseful, and phaseful is defined here. It's phaseful if what we get if we consider for a complete input the projection to the output for, I keep the example for the braking system, is the same as if we do the projection as defined here with the input projected to the handbraking system. What does this mean? It means that all the other input does not influence the handbraking system. So if this formula would be true, it cannot happen that the air conditioning system has a feature interaction with the handbraking system. So this proves that this function, which is related to this restricted syntactic interface, is independent of all the other input to the system. Okay? And this is the first definition, what it means that there is no feature interaction, which I found very important, because if I want to prove the safety of a handbrake system, I had to prove this. And just look at an example, airbag controller. Look at an airbag controller, and now I want to introduce a feature interaction. If an airbag controller would have no feature interactions, this would be the functionality, which means basically, and I keep it simple, that if there's a crash signal into the input, then this means there is an activate airbag signal in the output after 200 milliseconds. Maybe it should be 180 milliseconds, but this is typically what we expect when an airbag should be activated. And now the question is, are there feature interactions with airbags? I guess you all ride cars, as far as you ride cars, with airbags. And all these airbags, for all these airbags, we could now ask the question, are there feature interactions, influences the airbag? What do you mean?
Yeah, brake, for example.
Yes, seat belt.
It's a bit of a short answer. What does it mean, seat belt?
If you don't wear the seat belt, the airbag will not
come out. Is it a good idea? If you have a nasty driver who forgets to put on the seat belt, then he will be punished. So he even doesn't get an airbag.
In my opinion, yes, because sometimes. No, I have an answer actually. See, if you don't wear the seat belt, there is a likely chance that the airbag may kill you rather than saves you.
Because you think, because you move forward. Yeah, this is an interesting question, but this has also to do with modern airbags. Modern airbags even observe the behavior of the person, how fast it moves, and decides about the airbag movement according to that. So it's an interesting, difficult question. What are the feature actions we would like to have? But a good example would be that you say, if you're not driving faster than 5 kilometers per hour, then the airbag shouldn't be activated. That's a feature interaction between the input speed and the airbag. And if the airbag is deactivated, then it should not explode. I was involved in an investigation where a baby was killed by an airbag which was deactivated, and it exploded. And therefore, this is a typical example of a kind of a feature interaction which wouldn't work. I just want to give you the example how we do that. If we have such an airbag and we want to deal with a feature interaction, we introduce an additional input channel, which we can switch it on and off, which means we introduce an additional channel. And now we have to use this. If the airbag is if we have this, then at all times, only if on is true, the airbag comes out. So it's straightforward in our approach to do such a specification. And I promise to give you some numbers here. You have some real numbers. This is a truck company in Munich. This is BMW, which you probably know. And one of my PhD students, after I did the theory, worked out a more engineering-oriented approach to that. And a part of his work was to look at real systems to see how many features interaction was there. And he looked at two systems, which were subsystems of a truck and subsystems of a passenger car. So he had the number of systems was 55, the number of systems was 94. And now here you see the number of systems of this 55 with incoming dependencies. Incoming dependency means they have feature dependencies from other functions. And from 55 there were 36. Outgoing dependencies we had 29, and we have 27 functions here which had both incoming and outgoing dependencies. And only 17 functions of those were without any dependencies. And with the passenger cars, the numbers were even higher. Here you see the percentage. You get even a higher number. This is, by the way, shows that truck systems are simpler than passenger systems. And here you see we had around 80% incoming or outgoing dependencies. So feature interaction is a real issue in the industry. By the way, we have also done a PhD thesis which looked at the number of remaining errors in systems, and it's obviously that a very high number of remaining errors in systems are at the feature interaction. Why is that? Because systems are tested feature-wise. So you have a lot of test cases which just test the features, and often they forget about test cases which test whether feature A and feature B, which have a feature interaction, work together properly in cases feature interactions get activated. So it's a real issue. And this is the work of Andreas Vogelsang, quite recent. Here you see how we do the functional feature decomposition. So we have the overall systems and we decompose it into a number of subsystems. And here he introduced a data model for the modes, which describes the modes. So we have so-called mode models. And with these mode models, we can also introduce the dependencies between the different functions to understand how they are related. And we did some work with the truck company where we looked at their requirements documents to help them to find out problems according to feature interactions. And what we saw is that a lot of the problems in the requirements document had to do with those feature interactions. Here you see again the mode model. This is from a train we did together with Siemens, train doors, operation modes, and so on. I will not go into details, just to give you an idea how you can do that in a practical way. The idea, of course, is to form a functional hierarchy. And now we come back to my original question. My original question was, can we specify the overall behavior of a car with a formal specification? And I told you a few, I guess, 10,000s of pages of specifications, completely impossible. However, now, can we specify the behavior of a handbraking system? And the answer is yes. It takes maybe a few days and you have it. Can we specify the behavior of an automatic window? And the answer is yes. Can we specify the behavior of the radio in a car? And the answer is yes. So we can specify all those functions. And if we specify them together with their mode channels, we can compose them. And we get a specification of the overall car. And now, let's assume we have 4,000 functions. And let's assume it takes us 5 days a function. Then we have, as we simply can calculate, 20,000 person days to specify a complete car. Is that interesting for the car industry?
Is it not done by the AutoSAR, some standardization, this kind of specification?
No. Now let's calculate. 20,000 man days, person days. How many person years are that? It's a simple calculation. How many person days we have for a year? 200? 20,000 become up with 100 man years, right? 100 person years. How much money is 100 person years? How much is a person year? Well, about 100,000. It's not so important to calculate it very precisely. So it's about 10 million. Huh? 10 million to a complete specification of a car. How much is it to do the software for a car today?
1 billion.
Sorry?
I would say 1 billion. Maybe that's.
Depends a little bit if you take a premium class. Now the A8 comes out from Audi, and I would guess Audi paid about 2 billion. So 10 million is nothing. It's 0.5%. And I will come to that back. If you look at the benefits you would have from that, this would be very interesting. And this can only be done if you do this modular composition at the feature level, right? So this is an interpreted feature tree, which is very much related to what you know the work on FODA feature trees. And the FODA feature trees are uninterpreted feature trees. They don't specify the features. This would be interpreted feature trees. And now we can go into model integration. You have seen what I have presented is an architecture can be abstracted to an interface behavior. If we have an architecture and if we know about the interface behaviors of the components, we can calculate the interface behavior of the overall system. A state machine can be abstracted to an interface behavior. We even have proof techniques for implementation verification, and we can integrate further modeling concepts like message sequence charts or the action diagrams, process and process diagram services. So what we get in the end is an integrated view onto that. Interface at the composed system level, interface abstraction from an architecture to this, interface abstraction from here to this. And I remember I had this formula which I repeated at the beginning of this lecture, that if I do the composition of subsystems which are described by state machines, I get a big state machine from which I can do an abstraction, and I get an interface behavior again. So this is, for me, an important ultimate requirement on a modeling technique to have this semantic coherence. So it should be able to describe interfaces, to describe architectures, and to describe state machines. And it should be coherent in the sense that each state machine defines an interface. If you have the interfaces of the components of a system, you can calculate the interface of the system, and you can switch between composition of state machines and composition of interfaces. And I would claim if you have a modeling approach which does not support that, you have troubles. And now let's discuss what these troubles are. So a modular model-based system development. And now, how do we do that? We start with informal requirements. You always start with informal requirements. Sometimes if you use functions which are well known, you can also use those. And from that you do a specification. And here the specification is a specification of the overall system, and I just wanted to use this. This is this feature decomposition with feature dependencies. And now, by the way, now you are in a much better situation, because car manufacturers manufacture not only one car, they manufacture many cars. If they manufacture a lot of cars, I remember it's only 15 years ago, one of the main responsible people at BMW came to me and said, look, tell us, we are producing one generation of car after the other generation. From one generation to the next, there's a difference in functionality of about 10%. So we introduce some new functionality, but we keep a lot. but we redo 90% of our development. What is the reason? And the reason is that the car industry does the implementation of those systems at the level of hardware, CPU and buses, and does a whole high optimization of that. And therefore, for the next generation of cars, they have to use new CPUs, because CPUs are changed every 3 to 4 years. And when they use new CPUs, they have to redo all the process, because what they have as software is completely done for a particular CPU. And now let's assume we are able to do it completely at the logical level. Then 90% of what we need here is already there, because we take the classical braking function and we take the classical automatic window function, and perhaps we add an assistant function. And to add an assistant function means that we just have to specify this functionality and compose it. And here we are. And if we have this, of course, this allows us to do a lot of things, because depending on how we do it. And now we come back to the approach that I've told you about. How could we specify these functions? We could specify them by assertions. Then we can do proofs, not nothing more. We can specify them as state machines, which is equivalent, as we know, because the abstraction of a state machine is an assertion. If we specify all those by state machines, we can simulate the behavior. We can generate test cases. And therefore, we have a lot of interesting possibilities from that specification. OK, now we have the specification. What is the next step? And just to emphasize what I did here is I just specified the relationship of what's going on to the context of the system. Now we go on, we do the design. In the design, we do a decomposition. We discussed that right now, that of course design cannot be done automatically in general, so you need designers. Usually in a car company you have architectures which are used for quite a while, and you can use the same architectures. And now you do an architectural design. If you follow the systems engineering approach, what you do is you write specifications for each of the components. You could write them again as assertions, but you could write them also as state machines. And then you get an architecture verification condition, and this is here. Remember, this was S, the system specification, and now you have to prove that the composition of the components implies what is required by the system specification. If you want, you could try to do that by logical techniques. So you could try to use a prover. Sometimes it's useful, sometimes it's a bit difficult. But of course, if you have described the components by state machines, again, you can simulate those too. And then you can write test cases which test that. In any way, you can try to verify an architecture before you have built it. So you do architecture verification before you have finished the architecture. So you can be sure that you have an architecture which works. OK, now we have done the architecture. By the way, here I like to work with interaction diagrams, because this describes as a use case in a scenario the interaction between the different components. And this is typical for a car today. If for instance, let's assume this is a crash system, then we get the crash signal. And when we get the crash signal inside the car, a lot of interaction goes on, because a lot of the CPUs start and the functions on the CPU start to talk to each other. And finally, maybe this one says, activate airbags. And perhaps there's another signal that is needed. And finally, this says, make sure that the airbags comes out. So different to this, a lot of things go on inside. And you can describe this in scenarios. I've seen, for instance, with Daimler, once a description. This was an infotainment system. So they had about 600 scenarios like that to describe how the parts of the infotainment system work together. What's interesting here is that you can derive from this the behavior of this subcomponent. So again, there's a lot of interesting methodological approaches that can help here, because we talked about the design, so this would be helpful steps in the design. After having done that, now let's go to the implementation. What does implementation mean? Implementation means now for each of those components we have here, we produce implementations. So R1, R2, R3 are implementations. And of course, we want to verify these implementations. How do we verify them? We have to prove that from the properties of R1, the required properties of C1 can be deduced. And the same for the others. So this is component implementation and verification. And now we go on. Having done the implementation, we do the integration. Integration means now that we put these components together according to that blueprint which we have developed here. The architecture is now our blueprint, and we have done the implementation of the components, and we put them exactly this way together. So we have the integration, and we do the delivery. And in the delivery, we do system verification. And system verification means that we have to prove that the system as produced here fulfills the specification, right? And this is, I apologize for that, very much simplified, but exactly what you have to do in the systems engineering approach. Right. Now, the first question I have, what do I have to prove here? Which is proving also that the integration is right. Assume I have to verify my architecture, and assume I have to verify my components. What is left to prove here?
System functionality.
Interface verification.
Interaction between.
I have proved this, and I've proved this.
Interaction between components.
Nothing.
Principle there.
Nothing. Because my approach is modular. From here and here, this follows as a corollary.
No, but still there is a communication between two modulars. So when you integrate, so we have to check the. No, but we didn't integrate it there. So
This proves that the specified interaction between the components is good enough to guarantee the specification.
but it's only on the design level, right? At the integration.
This proves that each thing has a behavior like this. From the modularity, I know that if R1 implies C1, then I know that what is here is this one implies this one, and this one implies this, so I'm finished. And when I talk to people from industries, this is a moment where they consider me as being crazy. Because I say, you don't have to do anything about integration. Integration is for free. The correctness is for free. Theoretical, I'm correct.
But in practical case.
Practically, I'm not correct. Why do I'm not correct practically? Again, I tell you a story. I did a PhD with a guy for Bosch, and we wanted to find out how many bugs were in systems which are in operation in the market, and what are the reasons for that. And we were particularly interested in what are the architectural problems we found that way. And so my PhD went to Bosch, and Bosch was very good, very nice, and Bosch was not only paying for the PhD, they also allowed him to go to their archives, and he looked through their archives, looking at bugs that were around to find those bugs which were architectural bugs. And he did that for about 3 months, and then he came back, covered with dust, because the archives were very dusty, and I said to him, oh, now I'm really curious to find out how many architectural bugs you found. And he said, I don't know. And I said, what? You're working for 3 months on that and you don't know? And he said, well, I have the following problem. I find a bug here. System doesn't behave like that. And then I want to find out whether this is an architectural bug or whether it's a subsystem bug. However, in the systems that are produced by Bosch, the documentation of the architecture is not good enough. They don't describe the interface behavior of the subsystems. And therefore, I cannot distinguish whether a bug was a bug here in this step or whether it was a bug here. And therefore, it was not able to identify which bugs are there. And this is a bad situation in theory, in practice. And in practice, what happens is the following. They don't do a system specification. And therefore, they cannot even validate the system specification. They write lots of specifications informally. I've seen specification 14,000 pages long. Then they do an architectural design. This is mostly done by the OEMs, by the car manufacturers. The design is not done carefully enough to do an architectural verification. In the end, it's also not possible because the specifications are not good enough to do an architectural verification. So they have a rough idea of architectures, and then they give these different components to different suppliers. The suppliers get specifications which are also not very precise. And then they write their component implementations. Under the assumptions they understand more or less what is needed. And then they give it back to the car manufacturers and they do the implementation. And now you do an implementation with subsystems which usually don't fulfill this, even just assuming that this is there, but obviously it's not there, with an architecture which is also not properly defined, with a specification which is not really validated. And then you get in the integration, you get all the bugs that are there. Specification bugs, architecture bugs, and subsystems bugs. And the bad story is, which according to my PhD student, you really don't know. You find a bug here. It's obviously a bug. It's not so clear whether it's a specification bug, an architecture bug, a subsystem bug. Why is that a problem? Because then OEM should, finding the bug, either should change its architecture, getting a new specifications for some of its subsystems and then make sure that the subsystems are done the right way, or it should say, well, I want to have the subsystem changed. But it's not clear. So they go to a lot of interactions going on, and often they correct the bug and introduce another one, and they do it again and again and again, and the result is how much of the overhead in software design is according to integration in cars today? Up to 50%. 50% of the overall cost of software design in the car industry is integration. And the reason is because they do not manage that in a proper way. And of course, it's clear that you cannot do it in such a formal way how I introduced it. But the formal way tells you that in principle it's possible. It gives you the proof that the theory and the science behind it is there. And then, as I told you, if you work with state machines and you do some of those steps at least, you gain more and more possibilities. And there's not a black and white. It's not that you say either you do it or you don't, but you can do step by step in that direction. And that's something we hope that this will be done over the time. So where are we? I wanted to show you a complete and precise modeling approach. And of course, I didn't have the time to go in all the nitty-gritty details. You could talk for hours about all the details. But for me, it was more important that you get the idea, you get the clue. And the clue is, first of all, it's interesting to have mathematical models, which is very much to something which I liked always a lot, denotational semantics. Giving a mathematical model for what you do, which is a denotation. And I'm a big fan of the work of Dana Scott and colleagues in that. I believe this is something which is very helpful. But in addition, you need a logical representation, and you get immediately from this, you get a logical representation that allows you to do specification and verification. And as I told you, not very detailed, but at least I mentioned that you could also introduce a graphical representation for a structured definition of those systems. But again, I'm convinced you have to start here and then to think about this, not the other way around. If you look at state charts, for instance, or you look at UML, they did it the other way around. They introduced a graphical notation and then were trying to find a semantic model for that. And often they failed because it's much more complicated, much more difficult this way. And semantic coherence is what I introduced some slides ago, that those things have to fit together. And they would never fit together if you look just at graphical stuff. UML is just a very, just putting together. So it should not be called a unified modeling language because it's not unified. It's a united modeling language, like the United States. And so it's not coherent like the United States. So what can we do with it? Systems and software engineering, capturing properties and concept of systems. We have also done some tools. If you're interested, we have done experimental tools. Currently, they are further developed with Fortis. So if you're interested, I can give you some web addresses where you can try out those tools. Formal methods, yes, of course, you can prove to do proofs. You can also relate it to certain tools, and we have done that. And I'm most interested in this foundational framework, making concepts clear, proving that methods work. This is more or less what I wanted to say. I will close with a saying which is devoted to Mary Wollstonecraft. She's a British feminist. And she said, the power of generalizing ideas, of drawing comprehensive conclusions from individual observations is the only requirement for an immortal being that really deserves the name of knowledge. Thank you very much. Questions?
I have one question.
Yeah?
Related to the projection you mentioned.
That is.
Yeah.
Okay.
Actually, you have a system.
Yeah.
So when you decompose to a subsystem.
To a sub-function, you should say. Okay.
How do we call it as a projection? Is it not the contradictory word?
You ask whether it's a good title for it?
Yeah, kind of.
You can always discuss that, but it's a projection in the sense that you take a large behavior and you cut out a smaller one, and you cut it out according to a syntactic sub-interface. And so it's very much like projection in multidimensional spaces where you say, I'm only interested in a particular dimension. And this is why I call it projection. But you can debate that.
Projection preserves causality, right?
Projection preserves causality in the sense that you assume for this function causality properties again. That's right.
I don't get what's the difference between architecture design and integration. Like architecture design is just a mathematical model.
This is about this picture.
Yes.
And what's the difference between integration and architectural design? In a certain sense, it's two sides of the same coin, so it's very close together. But in architectural design, you have a large system, and you decompose it into subsystems. And it's a design in the sense that for each large system, you have a lot of different possibilities to decompose it. Right? So this is really a creative step in development. And currently, we are trying in the car industry to convince them to work very much with layered architectures, which is a design principle and gives you a particular form of architectures. When you have done that in a proper way and you have the architecture, then integration is not a real step, a creative step. It's a very simple step. You take what you have implemented, you put it together, and this is a blueprint. So it's not a creative step anymore. And what all you have to do is a quality assurance. So it's related, but it's different direction, so to speak. This is top down and this is bottom up. And it's not artificial that this is a V, so it's a V model. Okay? Okay, so thanks a lot. I wish you a good time for the summer school. I'm here about 1 or 2 hours more, and then I have to leave. I'm very sorry. I have a lot to do. Thanks a lot for your attention.
Thank you very much, Manfred, and a small gift from our university that we hope that you will like. Thank you.
Thank you.
Thank you very much.
Thanks a lot.
Thank you.